Good morning. I'm glad to be here today to talk about Cuda, OpenCL, and graphics processors. My name is Brian Catanzaro. I'm from NVIDIA Research. So today we're going to be talking about four main things. Firstly, I'm just going to go over some philosophy and some terminology and try to motivate why I'm excited about throughput computing, why I think GPUs are an interesting parallel platform for you guys to write code for. Then I'm going to be talking about actually how to do that using Cuda and using OpenCL. I'm going to be talking about how Cuda maps to NVIDIA GPUs to give you guys some leads on ways to optimize your code and get it efficient on GPUs. And then I'm going to close with a discussion of libraries for GPU computing, focusing on Thrust, which I think is a great place to start out for everybody who's learning how to use GPUs. So firstly, what is heterogeneous parallel computing and why do we care about it? Well, we care about it because of laws of physics. We are running into power walls. We just can't crank up sequential processors fast enough. And so we need parallelism. It turns out that you can optimize each of your cores in your parallel machine for sequential workloads. And you get one sort of processor, which is a latency optimized processor, and each of those threads are going to be really fast. But if you give back some sequential performance and focus instead on aggregate throughput, you can get a different kind of processor, one that's throughput optimized. It's scalable, it's very parallel, it's very power efficient, and you put those two together and you get heterogeneous computing. So we need both. We need sequential processors that can be fast to handle sequential workloads, and we need parallel throughput optimized processors for throughput workloads. And defining those a little bit, I always like to go back to an analogy from Seymour Cray where we talk about two kinds of workloads. One is plowing a field, and the other is combing through the field looking for all the seeds. So you can plow a field with a yoke of oxen, and you have a few of them, and they're really strong, and each of them does a lot of work, and you don't need that many of them, and you get the job done. On the other hand, for other workloads, where, say, for example, we're sorting through lots of data or looking for seeds in a field, you don't actually need a very strong processor to do the work. You don't need an ox. You need instead a lot of chickens. And so this analogy is basically that for some workloads we need lots of little cores, optimized for aggregate performance and de-emphasizing individual performance. So what does that actually look like in terms of processors? Well, this slide I show two sort of representative processors. The first one is latency optimized CPU from Intel, the Sandy Bridge EP. And the second one is our latest and greatest Kepler GPU, the K20. So if we look at the kinds of processing elements these cores have, the Sandy Bridge has 8 cores on the chip, and each of them can issue 2 SIMD instructions per cycle. And each of those SIMD instructions can be 8-way large. So you multiply that out, you get about 1,000-way parallelism. And it's running, about 100-way parallelism. And it's running at 3 gigahertz, so that's fairly quick. So that's a latency optimized core. A throughput optimized core, we have 14 SMs. Our SMs are the fundamental unit of our processors. It's kind of like a core. Each of them can issue 6 instructions per cycle, and each of those instructions are 32-way wide. And so that's much wider. It's on the order of 30,000 threads that are resident on the chip at any given time. But we're running much slower. So instead of running at 3 gigahertz, we're running at like 700 megahertz. So we have more parallelism, but we're going slower individually. In aggregate, we can still do some pretty amazing things. So if we look at single precision floating point operations, Sandy Bridge gets about 400 gigaflops per second, and Kepler gets around 4,000. Memory bandwidth, Sandy Bridge has about 50 gigabytes per second. The GPU has about 250. Along with this comes kind of an interesting difference in the memory hierarchy. So I was talking to David, and he told me you guys recently did matrix multiply routine, or Was I seeing a nod yes or no? That was yes. Okay, all right. Do yesterday. Oh, so it's fresh in your memories. So I'm assuming when you were working on this, you were thinking about SIMD, so how to use SIMD operations. And you're probably also thinking about how to use the memory hierarchy of the CPU. Did you do any cache blocking? Okay, all right, so you're familiar with this. So if we look at the memory hierarchy of the latency optimized CPU, it's what people have come to expect, where we have sort of these tiers, where every tier of the memory hierarchy that's closer to the actual units that are doing the work is smaller, and then they get bigger as you go out. So the register file is around 128 kilobytes. The aggregate amount of L1 cache, if you multiply all the cores together, is around 256 kilobytes. The L2 cache you get, that's a typo. It should be, no, that's right. Yeah, so it's 256 kilobytes per core, so that's around 2 megabytes in aggregate for the entire chip. And then the last level cache, we have about 20 megabytes. So that's the traditional sort of pyramid of the memory hierarchy. On the GPU, it's kind of tilted. It's kind of actually turned upside down. So the biggest part of the memory hierarchy on the GPU is the register file. So this Kepler GPU has 3.5 megabytes of register file, which is bigger than the aggregate amount of L1 cache, which is a little less than a megabyte. And the L2 cache is about the same size as the aggregate L1 cache. It's about 1.5 megabytes. So when you're designing algorithms to fit the GPU, they're going to be different, right? Because you're not going to be cache blocking in the same way. If you divide 1.5 megabytes of the biggest level of cache by 30,000 threads, there's just not a lot of storage per thread, right? So when you're thinking about the algorithms, you're not going to be blocking them in the same way. On the other hand, each of the threads can have a lot of state in the register file, so they can have a lot of private data per thread. Okay, so hopefully this discussion has given you kind of a sense that these two ways of looking at parallelism are really different, and each of them has their strengths and their weaknesses. So now I'm going to talk about why that's the case. So why is it that we have heterogeneous computing? The truth is that the different goals produce different designs. So many core CPUs, throughput optimized GPUs, they assume that the workload is highly parallel, whereas latency optimized CPUs have to be good at everything, whether it's parallel or not. And the goal of a latency optimized multi-core chip is to minimize the latency experienced by a thread. And that's why we have that cache hierarchy, and that's why we're so good at control, so all these branch predictors and so forth. Whereas the throughput optimized GPU, the many-core design, is going to try to maximize the throughput, lots of ALUs. We have lots of multi-threading to hide latency, so instead of using caches to reduce the latency, we're just going to hide it by moving on to the next available work item. And we won't have big caches. And we have a lot simpler cores, so they're not going to be working so hard to do things out of order and prefetch and predict branches and so forth. Instead, we're going to amortize the cost of control over SIMD. So SIMD is going to play a bigger role. And since you guys just did SIMD with your homework assignment, you're really familiar with what this is. So I'm just going to say SIMD architectures, we're using data parallelism. So we're trying to operate on vectors of data. And the reason why this is important is for area and power concerns, because we can amortize all the overhead of figuring out what to do over a big vector of work that we're actually doing. The downside of that is that the parallelism is exposed to you as the programmer, as you figured out in your last homework assignment. And I would actually claim that the SIMD parallelism is kind of neglected, so a lot of people just don't use it. So just as a show of hands, how many of you, for your homework assignment, was that the first time you'd used SIMD intrinsics? So most of you. How many of you had written a parallel program in the past at all? So it seems like there's quite a few of you that had written parallel programs but had never used SIMD before. And it's kind of a pain, especially when you're using intrinsics. I don't like having to use intrinsic for myself. And so a lot of times I would say that SIMD parallelism is neglected. Programming models like OpenMP or pthreads or MPI or the pgas languages, they tend to treat SIMD as a kind of parallelism that's orthogonal to their goals as a programming model. So OpenMP really doesn't say much about SIMD, neither do the pgas languages. And the idea is that you're going to be writing sequential code. It may or may not use SIMD internally, but the programming model doesn't have much to say about it. And the reason they do that is because it's difficult for a compiler to automatically use SIMD for traditional programming models. So like C, it's difficult to vectorize it and to automatically find ways of using those SIMD vectors in straight line code that somebody wrote. So the most common solution is that either people forget about SIMD and pray that there's a magic auto-vectorizing compiler that likes what you wrote and rediscovers the SIMD that was in your code. Or to instantiate intrinsics, which is almost like assembly language and can require a new code version for every new SIMD extension. So the processor vendors are always changing their SIMD instruction sets, and that can be a pain. For example, here's a brief history of x86 SIMD instructions that started out with MMX. MMX came out when I was in high school, which means you guys were probably still in preschool. But you know, ever since then, there's been this progression of SIMD extensions for x86 getting progressively more useful and progressively more feature-filled, adding floating point operations, adding horizontal operations. Now with AVX on Sandy Bridge, there's 8 wide operations. David told me that your homework assignment, you're using SSE, so that was the previous version, but Intel has moved on since then and has announced 3 more extensions beyond the SSE that you probably used in your homework. Additionally, there's Mike, which is an Intel project aimed at many core computing, kind of similar to a GPU, and it has its own SIMD instruction set. All right, so there's been a lot of different kinds of SIMD. A lot of times people don't use them, but that's becoming an increasingly big problem because if you just write code that doesn't use SIMD, you're leaving an increasingly large fraction of your throughput on the table. So back when it was just SSE and you could have maximum 4 wide SIMD vectors, if you didn't do SIMD at all, then you limited yourself to 25% of the throughput of the machine. But you know, 25% is great. I mean, if most of us got 25% of peak throughput on any code that we wrote, we would be really happy with that. And so that's why people just, you know, didn't worry about it. But as SIMD widths increase, now mainstream Intel processors are 8 wide. The mic, or what used to be called Larrabee, is 16-way. So there's an increasingly large percentage of the throughput of the machine that gets wasted if you're not using SIMD. And this becomes even bigger a problem if you had bigger SIMD vectors. So like NVIDIA GPUs are using 32-way SIMD vectors, and AMD GPUs use 64-way SIMD vectors. So you know, once the vectors start getting larger and larger, you just got to use them. And this problem composes with sort of the multi-core thread-level parallelism problem. So when I showed you those die photos, you know, there were 14, 15 cores on the GPU. Well, you've got to have threads to fill all those cores, and each of those threads has to use SIMD. So what we need is a programming model that addresses both. So a way to get thread-level parallelism and a way to use SIMD-level parallelism. And that's actually what Cuda was designed to do. And later on, what OpenCL was designed to do as well. And so the idea is that you have a special programming model for these heterogeneous architectures with wide SIMD parallelism with lots of parallel scalability. And the way that you're going to do that is by providing a thread abstraction for SIMD. So instead of using intrinsics, you're going to be writing threads where each thread is going to be mapped onto the lane of a SIMD processor. And then what you're going to do is structure your program so that you're writing in thread groups where you have you know, around 1,000 or less threads in one of these groups. And inside the group, the threads can communicate with each other, they can share data, they can have barriers, they can synchronize. Outside of those thread groups, you're going to be launching many of these thread groups when you invoke one of these parallel functions. You're going to forbid communication and synchronization in order to get scalability. So we're going to have both parallelism and SIMD together.
So from the perspective of NVIDIA internal person, is there a way to convince an NVIDIA GPU to accept a very, very wide SIMD extension instead of having these micro threads? Even if it's some hacked together way.
Okay, so let's see. So I guess the question is, you would rather program using intrinsics instead of microthreads?
Out of curiosity, is it possible?
Yeah, out of curiosity, is it possible? It's interesting. You know, I haven't actually seen people try to write an abstraction for GPUs that do that. I mean, I definitely could write one. I think the reason why people don't typically do that is because the threads that you get with Cuda, these micro threads that are targeting SIMD lanes, are more flexible than traditional SIMD architectures. So for example, you can have branches. You know, in SSE, it's awfully hard to have part of the SIMD vector do one thing and part of the SIMD vector do another thing. Whereas with GPU hardware, both from NVIDIA and from AMD and from other people, branching is part of the programming model. So you're actually allowed to branch. And what that does is the hardware will create masks that you don't have to manage as a programmer and execute both sides of the branch. And as you nest branches, it'll diverge and diverge and diverge, you know, until it potentially is maximally diverged. The hardware takes care of all that and takes care of reconvergence when you come back. So you can write code that targets these SIMD lanes that looks more like traditional code that has branches in it. Or that's pretty hard to do with a SIMD abstraction where you're just operating on SIMD vectors. So I think that's the reason why people haven't done that. But the great thing about these programming models, it's really easy to write libraries. I'm going to be talking about several libraries for GPUs. And if you felt really inspired about this programming model, you could write a library that did that and give it to people. So maybe that'd be an interesting thing to think about. Personally, I like Cuda the way it is, but you know, there's always room for improvement. So, but thanks for your question. I really appreciate it. Any other questions before I move on? All right. Okay, so what kind of language do you write when you're writing Cuda programs? You actually use C++. You know, you can use C. You can use C++ features like templates. You can have virtual functions and that sort of stuff. And let's see. OpenCL, which is a hardware and software vendor-neutral programming model inspired by Cuda, runs on a lot of people's hardware. So I'm going to be talking about that briefly as well. So most of my talk, I'm going to be talking about Cuda because that's what I use every day. I'll then mention sort of what the correspondences are to OpenCL in case you're interested in using those. Okay, so back to the programming model. I mentioned that you're going to write code where you have a hierarchy of concurrent threads. So you're going to launch a kernel, and each of them are going to execute the same program. And the kernel is going to be composed of thread blocks, and each of those thread blocks are going to be independent, but threads in the same block can cooperate. So when you're writing your code, you can query the runtime to see what your thread index is and what your block index is, and you can use that however you'd like. So you can use that to index into data structures. You can use that to branch to have them do different things if you wanted to. But everybody starts out at the same place when you launch the function. So what is a Cuda thread? It's an independent thread of execution. It logically has its own program counter. Even though it's being scheduled on a SIMD lane, you can diverge them all the way if you want. Just keep branching and branching until they're all the way branched. Each thread has its own variables, which are going to be stored in the register file. It has its own state, it has its own stack that sits in memory. Although one of the things people often get surprised by when they run Cuda programs is that when you launch 30,000 threads, the amount of memory that's required for your stack can be significant, right? Because all those threads potentially need to be resonant at the same time. So if you write a program that's very recursive, it could easily blow out the entire memory of the GPU just with all the stacks for all the threads that you've instantiated. Although there is a stack for every thread, you probably don't want to use it the same way that you would use a CPU thread, just because you're going to be launching so many of them in parallel. Cuda threads have no implication about how they're scheduled, so you're not allowed to assume that this block of threads is going to run before that block of threads. And this gives the runtime and the hardware a lot of flexibility to exploit parallelism, to get that throughput that is the goal of this entire machine. The way that Cuda threads are mapped onto NVIDIA GPUs, they're physically mapped onto thread structures that are instantiated on each of the cores. But you can also envision making them virtual, where, say, you had a block of threads. You could actually turn that into a single thread running on a latency-optimized core that had a loop that's just looping over all the threads. And that's kind of what OpenCL runtimes do when you write OpenCL code that runs on CPUs. So there's different ways of implementing it because of the flexibility of the model. So what is a Cuda thread block? This is a collection of threads that can synchronize. I like to think of it as a data parallel task. All the blocks in the kernel, they start out at the same place, but they can do anything they want. So you can have the beginning of your code be, let's have block 0 go do a matrix multiply, and block 1 is going to do a Fourier transform. That's totally legal code. They start out at the same place. They can go different places after that. The important thing, though, is that all of the blocks of the kernel need to be independent, and your program needs to be valid for any different interleaving of these blocks execution, and that gives you scalability. So the kinds of parallelism that you end up using when you write Cuda programs, you have thread parallelism, where every thread is independent. You have data parallelism, typically across threads in a block and across blocks in your kernel. And you have task parallelism in the sense that different blocks in the kernel can be independent. They can do different stuff. And also because you can launch multiple kernels onto the GPU. And if you launch them in separate Cuda streams, which I'm not going to talk about too much today, but if you're interested, the documentation's out there how to do this, you can actually get different kernels to be executing simultaneously on the same machine. So that's a kind of task parallelism. All right, so whenever we talk about tasks, we need to talk about synchronization. So Cuda provides a barrier for threads within a block to synchronize with each other. It's called sync threads. And what sync threads means is both a memory fence, so that all of the outstanding writes from all of the threads in the block are going to be visible to all of the other threads in the block, as well as an execution barrier, so that after the barrier, all the threads are going to be in sync. If you want your blocks to work together, you can have them coordinate with atomic memory operations. So let's say, for example, you had a shared queue, and all of the blocks are going to launch, say, 1,000 blocks, and each block is going to have 256 threads. And each of the blocks, as they process data, they're going to be appending to a shared queue. Well, you can use atomic operations to have each of the blocks compute how many items they want to add to the queue, then atomically increment a pointer, and then that sort of reserve space for that block to then save the data that it's created into this shared queue. So you can have the blocks coordinate to create data structures if you'd like, but it's not quite the same as cooperative execution because they can't really synchronize with each other. So that's the model. If you want a barrier between all your blocks, the way you do that is by terminating your kernel. So let's say at the bottom here I have two kernel invocations. First I'm going to do a vector subtraction between two vectors, and then I'm going to do a vector dot product between those two vectors. When I finish the first kernel launch doing the vector subtraction, by the time the second kernel is launched, all of the work from that first kernel is guaranteed to be completed. So the second kernel can then process the result. Yes, Jim?
So just to comment on the atomic increment to relate it to some notation from an earlier lecture. We talked about race conditions if you tried to do shared variable s equals s plus increment. An atomic operation will do that correctly. It will avoid the possible race condition.
That's right. That's right. So atomics are sort of race-free, but they're limited, right? So the kinds of things you can do in an atomic operation, they're limited to basically 64-bit words that you can do. So you can do things like add and subtract and increment. You can do compare and swap, which is useful as a general primitive. But you can't do like some arbitrary amount of work atomically. The granularity at which the hardware guarantees atomicity is going to be fairly small. Okay, so if you do want your blocks to coordinate in the sense that you have a set of blocks finish an entire computation and then another computation is going to consume that result, then you have dependent kernels and there's a barrier in between them that's there implicitly. Okay, so the blocks need to be independent. As I mentioned before, any possible interleaving of the blocks should be valid for your program. Your blocks are presumed to run to completion without preemption, but they can run in any order. They could run concurrently or sequentially. So you don't know when you launch it which of your blocks are going to be co-resident on the hardware at any given time. And this means that you can coordinate using a shared queue pointer like we've talked about, but you shouldn't write a lock. So if you wrote a lock, you could technically write one. I mean, we give you atomic operations. You can write a lock. But it's easy to make the machine deadlock if you do that because you don't know which of your blocks are actually resident. And if you have some set of blocks waiting for another set of blocks to finish releasing the lock, but those other blocks aren't even running on the machine because they haven't been scheduled yet, then you're toast, right? Just deadlock. So this restriction, it is fairly, it does mean a lot, right? This restriction does change the way that you write programs because you can't have the blocks interchange data and synchronize arbitrarily. But it does bring scalability. So when you write a Cuda program, you're fairly certain that it's going to run efficiently on hardware that could be vastly different in terms of its parallelism. So for example, we ship GPUs with all the way from 1 SM up to 30 SMs. So that's kind of like the number of cores. And the same binary runs on all of them. So when you write your Cuda program, you don't say like, oh, do I have this many cores? Well, then I'm going to launch that many threads. Instead, what you typically do is write the program exposing a lot of parallelism, whatever the parallelism is from your problem. Like vector addition is an easy place to start. If you have a big vector, you're going to launch work across the entire vector rather than launching work across the machine. And that brings you scalability, which is important. Okay, so I've been talking a lot about philosophy and sort of ways to think about Cuda, but I need to actually show you some code. This is vector addition in Cuda. So there's a couple things to notice. First, we have this global tag that we've stuck on the vector add kernel. And what the global tag says is this is a function that can be launched on the GPU from the CPU. Global functions always return void. So you can't return a value from the GPU. Instead, what you do is you operate by mutating some state. So in this particular example, we're going to be overriding vector C with the result of summing vectors A and B. And so if the CPU wanted to inspect the result, then you would know as the programmer, oh, I've modified the output vector, so I'm going to look in there to find the result. Okay, so that's the first thing to note is this global tag. The second thing to notice is that second line that says int I equals blockindex.x and so forth. What that's doing is using the indexing given to you by the Cuda runtime to figure out what thread you are in relation to all the other threads that have been launched. So we launch a certain number of blocks, and you're going to get an index into that set of blocks that you've launched. That's block index. Each of those blocks is going to have a certain number of threads. That's the block dimension. And then internally inside that block, each thread is going to have its own index. And so you can compute a global index by multiplying your block index times your block dimension and then adding your thread index. That'll give you sort of your global index across all the threads that you've launched. And once you've done that, then the element-wise vector addition is exactly what you would expect. Okay, so then we actually need to call this function. So we have our main function running on the CPU. And let's run, I didn't show memory allocation here, but let's assume that the data has already been allocated and initialized and so forth. Let's assume that we're going to launch, our vectors are n elements long, and we're going to launch work in groups of 256 threads. So the number of blocks that we're going to launch is n over 256, and the number of threads per block is 256, and those are the two arguments to the vector add kernel here. All right, so does anybody see the problems with this code? What details am I smoothing over that could get me in trouble? Yeah.
N is not divisible by 256.
Yes, good job. What happens when n is not divisible by 256? I'm glad you found that. That's a problem, right? So a traditional, a standard Cuda idiom, instead of doing n over 256, is sort of round up. So you divide n by 256, and then you add 1 if it wasn't divisible by 256 to give you sort of a number of threads that you know is large enough to cover the work that you have to do. And then to gate off the actual execution. So here you have your int I. Well, if I is less than n, that means that your global index is less than the number of elements in your vector, then you want to actually perform the work. If it's not, then you could be dereferencing past the end of the vector, which could end up with a seg fault, which would be bad, right? So you would just put a branch around that execution that says only do this if you're in range. So that's one of the problems with this code. I'll get to some of the others in a second. All right, so memory model.
So one more question
Yeah.
about that. So 256 is then the block dimension
Yes.
in the upper code?
Yes, that's right. So the second parameter, so this Cuda function launch that has these triple chevron brackets, the first parameter is the number of blocks to launch, and the second parameter is the number of threads per block. And that information gets propagated into the kernel. So when we say blockdim.x, the reason it's 256 is because that's how we launched it. If you wanted to launch it with a different number of threads per block, you could do that too at runtime. You can just choose a number and put it in there. Okay, so how does memory work in Cuda? Well, every thread has a per thread local memory. This is where the stack goes for every thread and other stuff like that. So if you have register spills and fills, that's where it would go. Every block has a shared memory, called per block shared memory, that the threads can use to coordinate and share data. And this memory is actually on chip, so using it is pretty fast. So a lot of Cuda optimization, it revolves around how do I use this shared memory in order to get my threads to coordinate, to reduce my traffic to off-chip memory by using more on-chip memory. So this is kind of like cache blocking, only instead of being a cache, it's managed by the programmer. So it's a scratch pad model. And then every device, so every GPU, has its own global memory. And the data in that memory persists across kernel launches. So you can launch one kernel, it produces some data. You launch another kernel, it consumes that data. It persists. But this memory is actually disjoint from your host memory. So this is the standard memory that you use when you write a C program that we call that host memory. And you need to use Cuda memcopy or something else that uses it internally in the library in order to transfer data back and forth between the CPU and the GPU. So how does that look? Well, let's look here. If we were going to use malloc, the traditional C malloc, for host memory on the CPU, what we would do is, let's say we have some vector size n. In this case, I'm going to make it divisible by 256, so I don't have to clutter up with the details of managing when you fall off the end there. But a traditional malloc, you just say the size of my data type times the number of data elements that I'm allocating for. I need to allocate that many bytes, and you ask for a pointer. And that will give you a pointer to host memory. Cuda malloc works pretty much the same. The only difference is that instead of returning a pointer when you call Cuda malloc, it actually modifies a pointer that you pass in by reference as a pointer. And the reason it does that is so you can check for errors. So if you try to allocate something that's really too big and doesn't fit in GPU memory, what happens? In a CPU, you would, well, there's various numbers of things that could happen. You can get an out-of-memory exception. Malloc could return 0. It just depends on the interface that you're using. For Cuda, the interface is that every Cuda call is going to return a Cuda error code, which could be 0 if the operation happened without a problem. So let's say your allocation was small enough, it fit, it worked. Then what gets returned is actually this error code. If not, then you can catch it and figure out what to do if you examine the result of the operation. So here when I call Cuda malloc, I'm not actually examining the result, so I'm just proceeding by faith that the malloc actually worked. Okay, so after I do malloc, then let's talk about memcopy. So Cuda memcopy, the first argument is the pointer of the destination. So here it's a pointer on the device. And the second argument is the source pointer. So here it's a pointer on the host, and then you tell it how many bytes you want to copy, and then you give it a direction. In this case, we're copying from the host to device. So Cuda defines that little enum that we're going to stick in there, and it'll tell it which way to do the copy. Then we do the kernel launch, and then we can copy the results back. And it's pretty much the same, except the directionality is reversed. So this is the hello world of how to manage data back and forth between the GPU's memory space and the CPU's memory space. Okay, so Cuda, in order to do all this, we have a few extensions to C++. So I talked about the global tag already, and that indicates this is a function that you can launch from the CPU on the GPU. There's also a device tag that you can add to a function, and this says this is a function that you can call from the GPU. So you can't launch a device function, but you can call it. So one good example would be like sine function, right? So somebody else wrote a library that does the work to compute sine of x, because actually that's pretty tricky. You know, writing your own sine of x function, that would be silly, right? None of us would want to use a programming model that didn't allow us to use somebody else's sine of x, right? So that's what device functions are for, that you can write functions in libraries and call them from other GPU code. So you are allowed to put the device tag on data. So this is global variables that live in GPU memory. Personally, I never do this because I hate global variables, but if you wanted to, you could. And then shared variables live in per block shared memory. Those I do end up using those because those are important for performance. This is how we use the on-chip memory, is we declare in our kernel that some data is shared. That data can be an array, so it's common to make an array that has an element per thread in your thread block, or multiple elements per thread in your thread block. That's how you declare it. Then we have a parallel kernel launch, so that's what that triple chevron is, and I've already explained that. Inside of your kernels, you have special variables for thread identification. So your thread index, where am I in the block? Your block index, where am I in the grid of blocks that has been launched? Your block dimension, how many threads are in each block? And there's also the grid dimension, so how many blocks did I launch? You can query all of those. And those variables are actually three-dimensional. So in the code that I showed you earlier with the vector addition, I treated them like one-dimensional variables, and if you notice, there was like blockindex.x. So that's for programmer convenience. I typically write code that is one-dimensional, so I launch one-dimensional arrays of threads. You can actually launch up to three-dimensional arrays. So you can have three-dimensional arrays of blocks, and each of your blocks can be three-dimensional. It just is sort of a convenience for dealing with indexing. So for example, if I was doing image processing and I wanted to launch a thread per pixel, it's kind of nice to have a two-dimensional indexing of my thread array. And so I can do that by, instead of using a single integer for how many blocks I want to launch, I can launch one of these dim3 objects where the first and second dimensions were non-zero. Okay, and then we also we have a few intrinsics, like sync threads, so that's a barrier between threads in a block. So how do we use per block shared memory? First, we can have just ordinary variables that are declared with this shared decorator. Then we can have sort of arrays that are going to be shared by the entire thread block. So for here, in this example, let's say I know that I'm going to launch the kernel with a block size of 256 threads, and I've defined that somewhere else as block size. I can say shared int, and then give it a name, and then block size. So that's how many ints do I want per block. That's going to be allocated when I launch the kernel. And then what I could do is, for example, have every thread figure out what its thread index is and load an element into that scratch. So that's kind of a parallel initialization of the scratch memory. And then I can communicate those with async threads. So if I execute the barrier, then all the other threads in the thread block are going to see that I've loaded the data in, and they can use that. And you can index into shared memory arbitrarily. So if you look in the middle of the screen here where it says int left equals scratch thread index -1, what that's actually doing is grabbing the value that my neighbor in the thread block loaded. So that's totally fine. You can index into it arbitrarily. And it does pretty well, even with fairly challenging access patterns. So the performance is pretty good. It's faster than the L1 cache. It's slower than a register file. The caveat is that it's fairly small. So on Kepler GPUs, the shared memory maximum size you can get is 48 kilobytes, but the register file is 256 kilobytes. So the amount of data that you can actually put in shared memory is small compared with the data that each thread can hold. So what that means is that I often use shared memory for communication and try to keep most of the data private to each thread. Okay, so what kind of features are provided for GPU code? Well, we have double and single precision math. It's IEEE compliant. We have the standard mathematical functions that are in math.h. We have atomic memory operations that can work on global memory. They can work on shared memory. So those are some of the things that are just provided out of the box. We also have runtime support to direct execution on the GPU. So we talked about Cuda malloc already. How do I allocate memory on the GPU? We also have free memory. There are different kinds of copies for copying data back and forth between CPU and GPU, or copying data on the GPU itself. And then there's some other things that are a little bit more esoteric and reflect the GPU's graphics heritage. So if you are doing visualization and you're writing an OpenGL code and you want to do some computation and then visualize it, then you can use Cuda GL map buffer object in order to sort of bind memory on the GPU to something that OpenGL can work with. And similarly, there's textures on the GPU. Textures are kind of a separate memory subsystem that's got a different set of caches. Sometimes people use those to improve performance, but it's just an optimization that you can use or not. Okay, so I've been talking about Cuda for this whole talk. Now I want to switch gears and talk about OpenCL for a moment. So OpenCL came along a few years after Cuda. People said, Cuda's pretty cool. I really like being able to program these throughput machines. The results I'm getting are really great. The only problem is that it's an NVIDIA-only thing. So how will we make an industry standard that everybody can use? And that's what OpenCL is. So there's a lot of companies on board. NVIDIA makes OpenCL work on our hardware. Intel makes OpenCL work on their CPUs. They've announced that OpenCL works on Xeon Phi, the mic architecture. Imagination Technology, which makes the GPU in many cell phones, including the iPhone, is on board. So future GPUs in your cell phone will be able to run OpenCL code, which is very similar to Cuda code. And a lot of other vendors as well, including even FPGA companies. So there's a lot of industry support behind OpenCL. And if you know Cuda, using OpenCL is fairly straightforward. the data parallel execution model is basically the same, only the words are slightly different. I would say one difference between OpenCL and Cuda is that Cuda's task parallelism model is based around sequential streams, where you have different queues that you can launch work into, and everything in a queue is going to run sequentially. Everything between queues is independent. Whereas OpenCL, you can actually create a directed acyclic graph of all the dependencies between your kernels and your memory copies and so forth, and explicitly build up that graph and give it to the runtime as a graph rather than a set of queues. So that's one nice thing about OpenCL. Okay, so this slide is mostly for reference. So if you decide after you've learned how to write Cuda code and you want to write some OpenCL code, these are sort of the correspondences between the two. So Cuda threads correspond to OpenCL work items, Cuda thread blocks correspond to OpenCL work groups, and so forth and so on. There are some things that make Cuda and OpenCL different. So Cuda supports C++ features like templates, which I find essential for writing libraries because they really allow you to reuse a lot of code. Without templates, you end up having to write your own template machines yourself using string manipulation, which is a lot more work. Also, Cuda is a single source model, meaning that you have one program. You can mix GPU code and CPU code in the same program. You compile it with a compiler, and then out pops a binary that you run. OpenCL is a dual source model where your GPU code resides in a separate file. And the way that you compile it is actually at runtime by reading that file into a string and passing the string to the OpenCL API, which then compiles it and builds up a kernel object that you can call. So that enforces sort of this rigid separation between what's my CPU code and what's my GPU code. So that's an important difference. Okay, so I started out the talk mentioning SIMD. So how does OpenCL and Cuda handle SIMD? Well, I'm going to talk in more detail about how Cuda maps Cuda threads onto NVIDIA SIMD hardware. But I wanted to mention how OpenCL handles it. And basically the answer is it depends. So every OpenCL runtime has a lot of flexibility. So OpenCL has the same model as Cuda that all the threads are independent and there's no execution ordering guaranteed by the model. And so that gives the implementation a lot of flexibility as to how to actually schedule the threads. And they use that to do different things. So AMD GPUs, for example, have 64 wide SIMD vectors. Currently, each of those SIMD vectors is scalar, just like an NVIDIA GPU. In the past, each of those SIMD lanes was actually VLIW parallel. So it was like 64 times 4 or times 5 elements per thread that you would need to do. And so when you're using that code, you would vectorize the code manually by using a lot of float 4 data objects or double 2 objects in your code. And then the runtime would be able to vectorize onto the SIMD hardware. The CPU runtime from AMD, you don't use vectorization at all. So if you, or the runtime doesn't do vectorization at all. So if you want to use SIMD, then you need to use explicit data structures that can be mapped onto SIMD instructions. So float 4 vectors, for example. So instead of doing like vector addition where every thread does one element, you would do vector addition where every thread loads 4 elements. Every thread does 4 elements, adds 4 elements, and then every thread stores 4 elements. And you do that by using these data structures that wrap that up for you. Intel has a CPU runtime that allows you to choose when you run your code whether it's going to use SIMD or not. So if it's not using SIMD, it's going to parallelize over the cores. If it is using SIMD, then it's going to try to take your OpenCL work items and map those into like the SSE lanes in your SSE or AVX instructions. In the NVIDIA GPU OpenCL runtime, it's fully vectorized, and this is how Cuda works as well. So generally, you write scalar code per work item. Okay, so now I'm going to talk about how to write efficient CUDA code. It's important to expose a lot of parallelism. So like I said, it takes order 30,000 threads to fill the machine. So you need to write programs where you launch lots of parallel threads. Yes.
Quick comment. So the students will get to use this on their next programming assignment because the GPU version, the particle simulator, is part of that assignment.
Great. So that means you should pay attention. Okay, so we need to have lots of parallelism. We need to maximize on-chip work. So per block shared memory is like on the order of 20 cycles to access it, whereas going to DRAM can be on the order of 600 cycles or longer, depending. So you really want to use on-chip memory register file. You want to minimize your execution divergence, meaning that the more branching you have inside of your SIMD vector, the more overhead there's going to be. You want to minimize your memory divergence so that groups of threads are going to be loading an entire cache line. And I'll talk about that a little bit more detail in a second. So how does this actually work? Cuda is designed to be functionally forgiving. The first priority is to get something to work. The second priority is to get it fast. So you don't have to know all these details in order to get your Cuda programs to work, but they're helpful if you're trying to get something to go efficiently on the hardware. And so the way that it works is every thread is mapped onto a lane of the SIMD vector. And we call the SIMD vector a warp. So this is just by analogy from weaving, right? If you have a bunch of threads together, they call that a warp when they're weaving a rug or whatever. So we call that a warp. On NVIDIA hardware, the warp is 32 elements. So that's a logical SIMD width. And then each thread block, which is a group of threads, is going to be scheduled onto a single SM and is going to reside there from when it's launched until when it completes without preemption. Peak efficiency requires multiple thread blocks per SM. And I'll talk about what that means in a second. So the GPU is really deeply pipelined, and we want to have lots of work resident on the GPU so that when one thread decides it needs to load from memory and it's going to take 600 cycles, instead of waiting for it to return, the hardware just moves on to the next waiting thread and starts executing that. So this means that your performance is going to depend on how many thread blocks you can have resident on the processor at any given time, because the more you have resident, the more you can hide the latency of talking to memory, the more your throughput can go up. And so what that means is that your resource usage per thread actually matters to performance, because the more heavyweight each of your threads are, the fewer of them can be fit onto the hardware at any given time, and then the fewer latencies you can cover. So that means if your program uses more registers, you're going to be able to fit fewer thread blocks onto an SM at any given time. If it uses more shared memory, then you're going to be able to fit fewer of them on at any given time. And so it's often worth trying to reduce your register count in order to get more thread blocks to fit on the chip. For Kepler GPUs, that's 32 registers per thread. Now, you guys are going to be using, David, I think you guys are using Fermi. So with Fermi GPUs, that was our previous generation, that number was about 20. So you had about 20 registers per thread before you ran into occupancy limits. Okay, so what is occupancy and how is it calculated? Well, basically what it is the hardware has some physical instantiation with some physical size. And those are going to impose a set of constraints on how much state each of your threads can use in order to get as many threads resident on the chip as possible. And as I said before, if they use more than that, then you're just going to have fewer of them resident at the same time, which is going to, in some cases, reduce your performance. So the first constraint is that the number of thread blocks per SM has to be less than or equal to 8. The number of warps per thread block, so this is how many threads can I put in a thread block, that has to be 1,024 threads, which is 32 warps. So you can have 32 or less warps per thread block. Each of the SMs has scheduler space for 64 warps. So that means that the number of blocks that are simultaneously resident times the number of warps per block has to be less than 64. So that's one constraint that could limit your occupancy. As I mentioned, the number of threads per warp is 32. And so if I multiply the register space for each thread by the number of threads per warp, by the number of warps per block, by the number of blocks on the SM, I get the entire amount of register state that's physically present on an SM at any given time. And on Kepler, the register file is 256 kilobytes large, and registers are reported in 4-byte blocks because it's, a 32-bit floating point is sort of the atomic data type of the machine. So 256 divided by 4 is 64K, so that means that you can have 64K registers per SM at any given time. So that's this constraint that you multiply all the state by all of the number of blocks that are resident on an SM. It has to be using 64K registers or less. And then the other constraint is shared memory. So the number of blocks per SM times the number of shared memory bytes used per block that you launched it with has to be less than either 48K or 16K. And that depends on a runtime setting. So by default, it's 48K. If you've decided that you want to prioritize space for the L1 cache, you can make the L1 cache 48K and make the shared memory only 16K. There's just a Cuda runtime call that you make to do that. OK, so then, yeah.
Here's a microphone.
So you mentioned the performance of L1 cache and shared memory is different, and shared memory should be faster. So, I mean, for now, you claim that you can divide the L1 cache to be some of the L1 cache can be shared memory. So, I mean, what's the difference here?
Yeah. So the L1 cache and the shared memory is physically implemented as a single 64 kilobyte array on the chip. But it's dynamically partitioned, and there's two ways to partition it. Either 16 kilobytes for L1 cache and 48 kilobytes for shared memory. That's the default. Or you can switch it so that it's 48 kilobytes of L1 cache and 16 kilobytes of shared memory. So it depends on the needs of your program. So if you decide I'm limited by my L1 cache because I'm doing a lot of register spills and fills and turns out that's more important, then you can prioritize it. You can just change the configuration. I would say for you guys starting out, the default setting is fine, so you don't have to worry about it too much. I'm just explaining this so you can come back to this slide when you're trying to figure out what the occupancy the profiler is reporting to you. You can figure out what that means by looking at these constraints, and you can adjust them as you optimize your code. Yeah.
So, I mean, the hardware implementation of these two arrays different, right?
It's just one array. It's implemented as one array. The reason why it's faster to access shared memory is because the hardware knows if you're accessing it as shared memory, and then it skips a bunch of steps. But otherwise, it's one single array. Great questions. Yes?
And I guess the constants for Fermi are somewhere else.
Right. Actually, if you go, I gave this exact same lecture last year.
We should look at those slides.
Yes, okay. The constants in my lecture for 2012 had the same things for Fermi. You can find this all in the NVIDIA documentation as well. I've just tried to digest it and put it all in one place for you on this slide. Okay, so I've mentioned occupancy. How do you actually find your occupancy? Well, there's a variety of profiling tools. So Cuda ships with a visual profiler. In this case, I've shown you a screenshot of it, and you can see a bunch of different kernels. You can see how long they took in sort of this timeline chart. You can sort them by their importance and so forth. And you can dive into the details. So you can look at any one of those kernels and ask the hardware to run different counters to figure out exactly what's limiting your performance. So that tool is pretty useful. I end up using it a lot. A simpler tool, which is also useful, is to just export CUDA profile equals 1 in your shell. And then when you run your CUDA program, there will be a file in that directory called CUDA profile sumnumber.log. The sum number corresponds to whichever GPU you were running on the machine. So a machine can have multiple GPUs. Typically, it's going to be 0, right, because you're launching work on the first GPU. And in that file is going to be a list of all the kernel launches that you made, how long they took, and what their occupancy was. And the occupancy is a fraction, it's somewhere between 0 and 1, and it's derived as I showed you on that slide before. So you can sort of use that to figure out what your limitations are and optimize your code. Okay. I'm going to skip that slide because we're running out of time. All right, so Kathy Yellick, professor here at Berkeley, made this great quip that a many-core processor is a device for turning a compute-bound problem into a memory-bound problem. And the GPU is definitely along this line. So in latency-optimized cores, you have a few cores, a big cache, and one DRAM. Throughput-optimized cores, you have a gazillion cores, and they're still just one bank of DRAM. There's just not enough space in the world to have enough pins for all of those processors to have their own path to DRAM. So what that means is that memory concerns often dominate CUDA programming. And it turns out that memory is SIMD too, although people don't often think about it this way. When you access element 0 on any processor, whether it's a CPU or a GPU, let's say you just want element 0, the hardware is actually going to load more than what you asked for. It's going to load an entire cache line. And this is kind of like a SIMD vector. And the width of that cache line is going to be dependent on the architecture of the processor. And it's just called the cache line width. So this has two effects. One is that if your threads are accessing sort of strided data sparsely, you're going to be wasting bandwidth because your thread's going to ask for element 0. The hardware is going to load 4 elements, but then you never use elements 1 through 3. They just get thrown away. So all that bandwidth was just wasted. So in this case, it was a quarter. Second, unaligned accesses can waste bandwidth too. So let's say that I want to actually use an entire cache line, but it's not aligned to the boundaries of the machine. Then I end up having to load 2 cache lines. So in this case, I'm using only half of the bandwidth. And since it's a throughput machine, it's often limited by bandwidth. So this is something that I always go to first when I'm trying to get my programs to go faster. How am I using memory? And how are my memory traffic requests interacting with the cache lines that the processor is using? So how does this work with SIMD? It turns out that each thread is presenting a memory request, like loading an element of data from a vector. The hardware on a GPU actually examines all the memory requests from the warp, so from your SIMD vector, and figures out exactly how many cache lines need to be loaded in order to service those requests. And that's what we call the coalescer. So it's nice, as a programmer, you don't actually have to manually prove that all of your accesses are unit strided and sequential and fit your cache lines well, as you would with a vector load intrinsic that would be much more inflexible. The hardware is dynamically discovering when your memory accesses are sequential, and in that case, it can just load 1 cache line for your entire SIMD load. If they're all different, it may have to load 32 different cache lines because each of your threads could be loading from some other place, right? So it has to be done dynamically. But in order to use bandwidth effectively, you should have your threads present as much as possible a set of unit strided loads that are dense and keep them aligned. I'm going to skip this slide. One typical thing people end up doing is transposing data structures. And this happens with CPUs when you're using SIMD instructions as well. So this is a generic transformation where you go from an array of structures to a structure of arrays. And what this allows you to do is when you do the loads, they end up becoming dense and sequential as opposed to being sparse. And that can be important for performance. OK, so I think I am done talking about Cuda. I'm going to move on in the last 15 minutes here to talk about thrust and libraries in general. So people often put efficiency and productivity at odds with each other. And we call this the abstraction tax. So you think of C, programming in C, you think, oh, it's an efficiency language. It's going to be fast. It's going to be low level. It's going to take me more work. But it's going to be efficient. Whereas something like Python is going to be high level. It's going to be slow. But it'll be easier as a programmer. We call this the abstraction tax, that you have to pay for more productivity is that it's going to be slower. I think in parallel computing, that's still true. But oftentimes, you end up either getting both efficiency and productivity or getting neither efficiency nor productivity, which I like to call the concrete tax. So you guys in your homework were just writing a matrix multiply. Did you benchmark it against MKL from Intel? And how many of you beat MKL? Well, I personally have never beat MKL. I mean, and Intel has like teams of PhDs that optimize MKL to death, and it's awesome. And using MKL, you should definitely do that. Like if you actually needed to solve a problem with matrix multiplying it, you should use MKL and not your homework assignment, although I'm sure you're proud of your homework assignment, and it does represent an achievement to have gotten the performance that you did. But still, it's way worse than what you get when you use the library. So I call this the concrete tax. If you write in a low-level language and you're very concrete and you over-specialize your code, and you just don't have the knowledge that somebody else does, you're concrete, but in the wrong way. And I think this is increasingly important for parallel architectures because the hardware is so different, the architectures are so different, the ways in which you can mess things up are so many more that it really pays to use a library. So I did a little study where I wrote some OpenCL code to do a reduction. So I'm taking a vector and I'm turning it into a scalar. And I ran that code. I wrote two different kinds. One of them was for the CPU, so I was exposing like 4 work items. So this is not very much parallelism, but enough to fill the CPU. And then I wrote a GPU one where there was huge amounts of parallelism, right? And then each of them was fairly well optimized, so I was getting like 80% of peak memory bandwidth when I ran the code on their respective architectures. So they were both pretty good. But then when I ran them crossways, so I ran the GPU code on the CPU, it was like 40 times slower because the CPU was all of a sudden managing 30,000-way parallelism, but it only has 4-way parallelism. So it had all these loops where it was looping over all the threads. And those were unnecessary. You don't really need those. Similarly, when I ran the CPU code on the GPU, it was 100 times slower because I had 4 threads and I needed 40,000, right? So I had over-specialized my code. So when you write low-level concrete code, it's really easy to over-specialize it, and then it's not performance portable. And often it's just not even performance at all, especially comparing to something like MKL. So we need abstractions at many levels in order to solve this problem. We need primitive computations like BLAS operations like your matrix multiply. We need data parallel primitives like prefix sum. And I think we need things like domain-specific languages. And these abstractions make parallel programming both more efficient and more productive. So if there's anything that you get from my talk today, use libraries whenever possible. If cuBLAS provides matrix multiply, use that. cuFFT provides Fourier transforms. Or Thrust, which provides data parallel primitives. And that's what I'm going to talk about for the next few minutes. So Thrust is a C++ template library for Cuda. It mimics the C++ standard template library. And so it provides containers. The containers are typed for the host or for the device, which allows the memory transfers to be hidden. So as a programmer, you don't have to worry about them. It provides algorithms like sorting, reductions, and scans, and so forth. So here's some Thrust code. So this is actual functional code that runs on the GPU. You can create a Thrust host vector of ints. That's going to allocate data on the host. Here I'm allocating 32 megabytes or 32 million integers. I can call Thrust generate, and you see I'm giving it the begin and the end. So this is like the standard template library in C++ of that vector. And I'm giving it the standard clib rand function. And it's going to call rand and generate an element and store it in that host vector for every element the host vector contains. So by the time that generate statement's done, I have 32 million random numbers. Then transferring the data to the device, instead of calling Cuda memcopy, it's all handled by the type. So I have a Thrust device vector, and I just assign it from the host vector. And Thrust, because the types are different, it statically invokes Cuda memcopy. So you don't have to worry about the memory spaces as much. Then I can run sort. So for example, I just call Thrust sort. I give it the begin and the end. And after that, then the data is going to be in sorted order. And then I can either assign the data back to the host vector, or I can call a copy routine, depending on what I'd like to do. So that's what a thrust program looks like. The objectives are to improve program productivity, encourage generic programming so that you can reuse code, so you don't have to write stuff over and over again, and to make it high performance. Thrust containers avoid common memory management errors, so it's really common when you write code to forget to free it if you explicitly called malloc. Well, with Thrust, you don't call malloc, you just allocate a container, you construct it. And when you construct the container, it allocates the memory, and the container is automatically destructed with C++ standard destruction rules, and when that happens, the memory is freed. So you don't have to worry about managing memory. You also don't have to worry about segfaulting because you dereferenced a device pointer on the host. You know, if you have a pointer that points to something in GPU memory and you dereference it on the host, you're going to get a segfault. But if you have a thrust device vector and you dereference it on the host, it statically knows that Cuda mem copy is necessary and will do that mem copy for you, and you'll get the right answer. So I didn't have to, allocate space on the host and call Cuda mem copy and print out the temporary that I had done on the host. I just dereference the device vector right from the host, and it works. Okay, so Thrust is built out of iterators like the standard template library. A pair of iterators defines a range. So you can call algorithms on the range. So for example, reduce, you give it a pair of iterators, the begin and the end. And iterators are kind of like pointers. You can increment them, you can dereference them, and you can subtract them. Those are the three main operations that you can do with any sort of pointer. And you can also do them with Thrust iterators, standard template library iterators. But they encode a lot of information additionally than a pointer would, and it's all done statically. So for example, Thrust will launch algorithms based on the type of iterators you give it. So if you have iterators to data on the GPU and you call reduce, then it's going to launch a parallel reduction for the GPU. It has enough parallelism to fill the GPU. And that's very different from the kind of reduction that you would launch on the host. But the code looks exactly the same. The only difference is that you're passing in iterators of different types. The device iterators are on the GPU, the host iterators are on the CPU. So the kind of algorithms Thrust provides, there's for each, transform, gather, and scatter. Those are element-wise. There's reductions like reduce, prefix sums, sorts. So for example, to call an element-wise operation, this is sort of a vector addition in one line. If you look at that transform that says a.begin, a.end, so that's the range of the input that I'm going to be performing this transform over. Then I give it another input, b, and I give it an output iterator, c, and then I give it a function that's going to be invoked at every element. In this case, it's plus. And then if I wanted vector subtraction, it would be the same code. I would just instantiate it with a minus operator. If I wanted to do a multiply reduction, like for example, for a dot product, you could do that with reduce, where or sorry, this wouldn't be a dot product. If you wanted to multiply all the elements of a vector together, you would just hand in a multiplies reduction operator into reduce. Okay. So Thrust algorithms work on standard data types like ints and floats. They also work on custom types. So let's say I had a float2 type it was like a struct that had 2 floats in it. I could make a negate operator that's just going to negate both elements inside that struct. And I can call transform using my custom operator. Here's a sort with a custom sort operator, so you can make your own struct and sort it based on one of the fields in that struct if you'd like. You just have to instantiate the functor yourself and pass it to sort. You can interoperate with Cuda code. You can use a Thrust raw pointer cast to get a Cuda pointer that then you can pass into any Cuda kernel. So as you guys work on your homework, if you need to write your own Cuda kernels, you can still use Thrust for memory management, for like printing out results if you need to debug something. It's really easy to do that, and you can still call your kernel code. Yes.
So can we say whether this is already installed on Fermi?
Yeah,
Fermi at NERSC?
It's installed. Thrust is part of the standard Cuda distribution, so you don't have to do anything to install it, and it runs fine on Fermi. You know, the only difference when you do something like this with a raw pointer is that if you dereference it on the host, you're not going to get that good behavior where it does a CUDA mem copy automatically, because the type of that pointer is just like any other host pointer, and you're going to get a segfault. So if you sort of escape thrust, then you have to know what you're doing. Okay, so CUDA is a very explicit parallelism model. You launch threads, right? You launch blocks of threads. It's your responsibility as a programmer to schedule everything, to decompose your algorithm, and to launch the work. Thrust is more implicit. So the operations themselves are explicitly going to be implemented in parallel, but the work you do as a programmer, instead of doing this decomposition where you figure out how many threads and how many blocks and so forth, and you know, check to make sure you're not over the end of the vector if your number of elements is not divisible by 256 and all that, right? Instead of doing that, you just write a functor. In this case, this is for Saxby, so I'm going to scale a vector by a scalar and add it to another vector. You create the functor, and it carries inside of it the scalar, so you close over that scalar. And then the element-wise computation you just write as a callable operator. And then you call transform, and you instantiate one of these functors with the scalar that you're using to do the scaling. Now, if you look at this code, there's no parallelism explicitly in this code, right? You don't say how many threads you want. But it knows how many threads you need, whether you're running it on the CPU or running on the GPU. The CPU backend actually is parallel. It uses OpenMP. So you can get parallel CPU code. This is parallel CPU code, as well as parallel GPU code, the same code. Okay, I'm going to skip this. Other than to say, you know, it's way more productive to do this than to write your own algorithm. So like serial reductions, it's like one line of code if you're writing a loop that reduces a vector into a scalar. If you write it in Cuda, it's going to be pages of work, right? Because you have to divide your vector into blocks, reduce each of the blocks separately, then launch another kernel that reduces the temporary results from each of the blocks, and so forth. So it's a lot of work. But if you call thrust, it's really easy. It's just all bound up. You just call reduce. Sort is really great in thrust. It's super fast. It has all sorts of wonderful properties that I don't have time to explain. It's on GitHub, so you can check it out. It comes along with Cuda, so it should be installed for you automatically. And I highly recommend it. I use it all the time. Even when I'm writing my own custom Cuda kernels, I still use thrust because the memory management and the ability to print out stuff from the GPU directly is just really useful. Okay, so I'm out of time. I hope from this discussion today you've gotten home, you've brought home a couple of points. So firstly, that latency optimized computing is different from throughput computing. Both of them have their place. They complement each other. There are programming models like Cuda and OpenCL that allow you to use throughput optimized computing. They abstract over SIMD, so you don't have to write intrinsics. You get that along with your program for free, although the details of how that works can sometimes be a little complicated. And they encourage you to write SIMD-friendly, highly scalable algorithms, which I think is important regardless of what platform you're running on going forward. I mean, SIMD widths on CPUs are going up. So parallelism on CPUs is going up. Parallelism and SIMD on GPUs are going up. This is just the laws of physics. So writing Cuda programs helps you to think in a way that scales to the future. And then finally, use libraries. It's a great way to capitalize on the hard work of other people. And Thrust is a great place to start. It's where I start all my Cuda programs. So with that, I'm out of time. But feel free to ask me any questions. You can send me emails if you have questions. I'd be happy to answer them.
So let's thank the speaker. So just one comment and advertisement. You didn't mention the currently fastest computer in the world on the top 500 list is GPU-based.
That's right, Titan at Oak Ridge. It has 20,000 Kepler GPUs in it, and it's super awesome.